Today we are going to discuss about the performance parameters of the chopper circuit. Okay, so we see that the power semiconductor devices require a minimum time to turn on and turn off. So in case of chopper, we see that there is a term duty ratio or duty cycle, which is nothing but the ratio of on time by the total chopping time. Okay. And keeping a maximum value of Kmin and a maximum value of Kmax, and thereby limiting the minimum and maximum value of output voltage. So the switching frequency of the chopper is limited by controlling the duty cycle K. Okay. It also been noticed that delay max, which is nothing but Vs by 4FL, as frequency is limited, means the switching frequency of the chopper is limited by limiting or by varying the K, and the ripple current, load ripple current, which from the equation we see that the load ripple current is inversely proportional to the frequency. So the frequency should be as high as possible to reduce the load ripple current and to minimize the size of any additional series inductor in the load circuit. So in case of chopper, there is only one thing. If we can limit or control this thing, that means the duty cycle K, then we can limit everything. Okay. Then we are going to discuss about the multi-phase chopper. In case of normal chopper circuit, which we have been discussed before, we see that there is only one power semiconductor devices and a freewheeling diode, means a switch and a freewheeling diode or inductor. But in case of multi-phase chopper, consists of two or more choppers connected in parallel. When two choppers are connected in parallel, then this circuit is called a two-phase chopper. So the figure here, which figure is shown here, it is a two-phase chopper, as there is, this is one chopper circuit, and the another one is, okay. So here two chopper circuits are connected in parallel. That's why it is called a two-phase chopper. When there is a three chopper circuits or three choppers connected in parallel, then that is called a three-phase chopper. Similarly, up to n-phase chopper are available. Okay. So a multi-phase chopper may be operated in two modes, that is in-phase operation mode and phase shifted operation mode. So what do we mean by in-phase operation mode and phase shifted operation mode? In the in-phase operation mode, what happened? All the parallel connected choppers are on and off at the same instant. So there, in this figure, there is two choppers which are connected in parallel. So in phase operation mode, what happened? Two parallel connected choppers, in both the choppers CH1 and CH2 are on and off at the same instant. So we are go through the graph, then it is clear for us very much. So this is I1 and this is I2. So in phase operation mode, what happened? This I1 means when the chopper CH1 is on, the current flowing through CH1 is I1. So this during this time CH1 is on and a current is flowing I1. In the same time, the CH2 is on and a current flowing through CH2 is I2. So this is I2. So what is the actual value of output current? This I1 plus I2. That means 2 of I0, because this is the value I0, I0. So 2 actual the actually the output current becomes 2 I0. Okay. This is the in phase operation mode. Then what do you mean by phase shifted operation? In the phase shifted operation mode, what happens? Different choppers are on and different choppers are on and off at different instants of time. Okay. So so from the graph we can easily see in that during this time during this time period CH1 is on and the current flowing through CH1, which is I1, nothing but the value of I1 is maximum value of I1 is I0 during this time period. Okay, the CH2 is on and this value of CH2, sorry, the current value of maximum value of I2 is I0. Okay, so if we combine these two graphs to finding out I, the load current, what happens? We get this type of curve. Okay. So here the off time gets reduced. So in the two-phase chopper configuration, inductance L in the series with each chopper means the inductance, this inductance, we assume that these two inductance have sufficiently large that the chopper operates independent of each other. As these values are very much high, so each of the chopper can operate independent of each other. Okay, and the figure we have seen, that means the graph, we have do this graph for the duty cycle is 30%, K is 30%, means Q is 0.3. So for in-phase operation, we seen that the input current is obtained by addition of I1 and I2 and it's seen to be doubled as shown in case of in-phase operation. Okay, and the in-phase operation of multi-phase chopper is equivalent to a single chopper operation. Single chopper operation. Okay, and from this figure, we can see that the frequency of input current is doubled and its ripple current amplitude, that means I max minus I min, is half as compared to in phase operation. That means in this case the frequency of operation it gets doubled. As the frequency of harmonics in the input current is twice the switching frequency, then what happens? When the size of the filter is reduced in case of phase shifted chopper. Okay. This shows that phase shifted operation of multi-phase chopper is usually preferred. For what reason? For the reduction in the size of the filter. Okay. Then we draw a graph for k equals to, this graph is k equals to 0.5, that means 50% duty cycle, and this graph is for 60% duty cycle. Okay. So here we see that for the 50% duty cycle and of phase shifted operation, the output current is continuous and without any ripples. Okay. But for 60% duty cycle, we see that the supply current I, this is I and this is I2, is continuous but with a pedestal of half load current. Okay. So a multiphase chopper is used where large load current is required. As we do the operation of parallel alternators or parallel transformers, the same reason we use a multiphase chopper. So what is the function when the large load current is required? Then we use the multi-phase chopper. The main advantage of this chopper over a single phase chopper or single chopper is that the input current has reduced ripple amplitude and increased ripple frequency. All are written here. Okay, there is no problem. Input current has reduced ripple amplitude and increased ripple frequency. Okay, and as a consequence of it, the size of filter for a multiphase chopper is reduced. There is an advantage. So what are the disadvantages? Here extra communication circuit require additional external inductor required and complexity in the logic circuit, means in the control logic. Okay, so now we are going for discussing the last part of the chopper circuit, which is nothing but switching mode regulator. DC chopper circuits can be also used as switching mode regulators to convert a DC voltage normally unregulated to a regulated DC output voltage. Means it regulated normally convert a DC unregulated to a regulated DC output voltage. The regulation is normally achieved by PWM, means pulse width modulation technique, which we are discussing before, at a fixed frequency. And the switching device is normally a power BJT or a MOSFET. Now, we see that the output waveform of a DC chopper with resistive load is discontinuous and contains harmonics, and the ripple content is normally reduced by using an LC filter. Okay, so by using an LC filter, we can eliminate the ripple content of the chopper circuit. So this is the basic elements of a switching mode regulator. What are the elements? Here we give the supply. This is a DC chopper. Here is a we get the output, and from a output there is a feedback with a reference. Okay. Then this is the error. This error is amplified by an amplifier. Then we get a control we, we get a control of this error circuit, and then this is fed to the DC choppers. Means here we get the unregulated supply. So the switching regulators are commercially available as integrated circuit. The designer can select the switching frequency by choosing the values of R and C of oscillator period should be about 100 times larger than a transistor frequency time. For example, if a transistor has a switching time of 0.5 microsecond, then the oscillator period should have 50 microsecond, means 100 times, which gives a maximum oscillator frequency of 20 kilohertz. So the oscillator frequency must be as high as possible. Okay. The transistor switching loss increases with the switching frequency and the efficiency decreases. In addition, the core loss of the inductors limits the high frequency of operations. So, in core of the inductor have some losses, and this limits the high frequency operations. So, these are the main funda of regulating circuits. Okay, that means switching mode regulators. So there are mainly four basic topologies of switching regulators. Number one is the buck regulator. Number two is the boost regulator. Number three is a buck boost regulator. And number four is a cuff regulator. Cuff regulator is named after its inventor, name of its inventor. Okay. So at first we discuss about the buck regulator. So this is the main circuit of the circuit diagram of buck regulator. Here we use a transistor Q1. Okay, this is a transistor which is denoted by Q1. We give a supply current, supply voltage Vs, and therefore a current Is is flowing through here, and this is also same as an average current. There is a freewheeling diode Dm. There is an inductor value high valued inductor, and the current flowing through inductor is small IL, and capital IL is the maximum value of inductor average. There is a load, and in parallel with the load there is a capacitor. The current flowing through the load is IA, okay, and IC is the current flowing through the capacitor. There is a feedback after the inductor and before the connection of the capacitor, and this is a control circuit which is then fed to the transistor. In the transistor, input is the control logic. So what happened actually happened in a buck regulator. The average of the average output voltage is nothing but VA, okay, or VO. In a buck regulator, the average output voltage VO is less than the input voltage Vs. So here VO is less than Vs. This condition we are seen in case of a step down chopper. Okay, that's why it is the word name used as buck. As V0 is Vs, that's why we call this a buck regulator. And this is also like a step down chopper. So, in case of normal chopper circuit, here also there is a two circuit operation. Okay. So, mode 1, when the transistor Q1 is on at T equals to 0. Then the circuit becomes on, means this becomes short. Okay. There is a capacitor load this, and this diode does not work, means this freewheeling diode does not work when the transistor Q1 is on. So this is the mode 1. This is very clear. The input current to the end here, Is is nothing but IL. So the input current which flows through the filter inductor L rises. Simple. As the time increases, the current through the inductor also increases. That means rises, and which flows to the filter inductor, filter capacitor, and the load resistance R. Then mode 2. What happened in case of mode 2? Mode 2 is consisting of only these circuits. The circuits which are within a rectangle or within a box, this circuit is conducts when the transistor Q1 is switched off at T equals to T1. That means the mode 2 operation. So this is a mode 2 operation. IL is flowing through here, IC, I0, IA, and the freewheel diodes conduct due to the energy stored in the inductor, and the inductor current continues to flow through the L, C, and load and the diode DN. And the inductor current falls until transistor Q1 again switched on for the next cycle or in the next cycle. So inductor stores energy at the time from the time t equals to 0 to t equals to t1. So at t equals to t1, when the transistor q1 is switched off, then due to the energy stored in this inductor, the freewheeling diodes starts conducting. Okay, and this inductor current flows through inductor, capacitor, load, and this freewheeling diode. So the inductor current falls until the transistor Q1 is switched on again in the next cycle, because the energy is going to reduce. Okay. So now, depending on the switching frequency, the filter inductance, capacitance, and the inductor current could be discontinuous. Okay. So now we go through the equations, what happened in mode 1, mode 2 operations, and then the waveforms of a buck converter. So from the mode 1 operation, we can easily say that the voltage across the inductor L is nothing but EL is equals to L di dt. Assuming that the inductor current rises linearly from I1 to I2 in the time T1, that means Vs minus VA is the output voltage, is equals to nothing but L into I2 minus I1 by T1, which is equals to L del I by T1. Okay. So from this equation, that means Vs minus Va equals to L del I by T1, we get the value of T1, which is nothing but del I L by S Vs minus Va. And again we seen that the inductor current falls linearly from I2 to I1 in the time T2. So we can say that VA is equals to L di T2. That means T2 is nothing but del I into L by VA. Okay. So here we get the values of del I. In both cases, del I is common. So if we equating the values of del I in equation 1 and equation 2, we get that del I is nothing but Vs minus A Va into T1 by L into equals to Va T2 by capital L. Okay. So, substituting the value of T1 equals to Kt, as we know that K is a ratio of T1 by total T. Therefore, T1 is nothing but Kt and T2 is nothing but T minus T1, that is 1 minus K into T, gives the average output voltage. Va is nothing but K into Vs. So, from assuming that the transistor is a lossless switch, therefore the input power equals to the output power. So we giving put the value of VA here, that is VSIS equals to VAIA equals to KVSIA. Therefore the average current is IS, which is nothing but K into IA. That means now we can say that the total switching period T is nothing but 1 by F, which is nothing but T1 plus T2. So from the equation we get in here, we get the value of T1 is nothing but del I L by V S minus VA and T2 is del I L by VA. Okay. So from here we put the value of T1 and T2 and get this result, which gives the peak to peak ripple current del I. Okay. From here we get that peak to peak ripple current as VA into VS minus VA by VS. Then we put replace VA by K. Then we get this value. Using the frequency del I is equals to Vs into K into 1 minus K by Fl. Now we are using KCL. After using KCL, we find that load current IL is nothing but IC plus IO. Now, if we assume that the load ripple current del IO is very small and negligible, then del IL is nothing but del IC. Therefore, the average capacitor current which flows for the time period T1 by half, T1 by 2 plus T2 by 2, which is T total T by 2 is nothing but del I by 4. Okay. So now the capacitor voltage which stores in the capacitor is expressed as DC is equals to 1 by C integration ICDT plus DC at means initial voltage at time t equals to 0. From there we get the ripple peak to peak ripple voltage of the capacitor, which is nothing but del I T by 8C. Okay. So del VC is nothing but del I by 4 del I by 8 FC. Then substituting the value of del I here and we get these two equations. Okay. So the what are the advantages of buck regulator? It requires only one transistor. It is simple, has high efficiency. The DIDT of the load current is limited by the inductor. However, the input current is discontinuous and a smoothing input filter is normally required. It provides one polarity of output voltage and unidirectional output current. It requires a protection circuit in case of possible short circuit of the diode path. That's why we using a freewheeling diode. Okay. So these are the curve. This is the output voltage. Okay. Then the inductor current during the T on increasing then decreasing. Okay. This is the average average output current, that means this is increasing, but during the transistor off period this is 0 and then again increasing. Okay, so next is I2 minus Ia and I1 minus Ia. This is another graph, and after that we get the value of Vc. This is a Vc which almost sinusoidal, and this is the output current IO, which is nothing but IA. Okay, this is a continuous curve, and there is an example. In these examples, Vs, del Vc, del I, F, Va all are given. Okay, then we have to find out Va del I. From the formula we get all the things. Okay, so up to this, today we are stopped here.